Hey guys, so this is part 2 of chapter 3. We already went over basically just briefly listing the different kinds of the 4 different biological or organic molecules that we have out there. These include carbohydrates, nucleic acids, lipids, and proteins. And now we're going to basically delve into them a little bit more. The first one that we're going to be doing is a typical macromolecule. So if you remember, out of those 4 large biological molecules, 3 are actually macromolecules. And what I mean by macromolecules is that they follow the whole monomer equals, like many monomers equal a polymer rule. So a macromolecule is going to have similar building blocks or monomers that come together. They're joined together through a dehydration reaction, and then we get the full polymer, right? So a carbohydrate works pretty much this way as well. We have specific building blocks of carbohydrates, and then when the monomers come together, they form the polymer. So carbohydrates are organic molecules that always contain carbon, oxygen, and hydrogen. And usually these are the only 3 atoms that we actually find in carbohydrates. They're also known as sugars. If you've ever noticed, whenever you eat like a carb, so I'm sure everyone here is familiar with carbs. You think of like bread or pasta, right? And yeah, I'm sure everyone's familiar with carbs. So what carbohydrates are actually sugar. So when you eat like bread, if you ever have the actual patience of and restraint of not actually eating, chewing the bread and swallowing it immediately, you may notice that the bread slowly becomes sweet in your mouth. That's because carbohydrates are sugars. And so another way to call these carbohydrates are saccharides. Saccharide in Latin means sugar. Okay, so saccharide kind of sounds a little bit like sugar, right? So that shouldn't be too hard to remember, hopefully. So these include very simple sugars. So carbohydrates include simple sugars, so the building blocks of the sugars and the polymers of the sugar, so the monomers and the polymers. In animals, carbohydrates are a primary source of dietary energy, and they're also the raw material for manufacturing other kinds of organic compounds. So usually the carbs that we ingest basically are used for energy purposes. And then in addition, they can also be used as other, raw material to make other things from them. So other things can be made, they're like the smaller little material that is needed to make other bigger things. So like other bigger structures like organelles or whatever have you. In plants, carbohydrates serve as a building material for much of the plant's body. They also serve as an energy source, but plants especially, we'll see it in just a second, they have a specific kind of carbohydrate that is extremely important to them. Without it, they really wouldn't be able to survive. Almost all carbohydrates are hydrophilic molecules. That means that they readily dissolve in water. So hydrophilic, okay, means that they are water loving. So hydro means water, okay, and philic comes from the word philia in Greek, which means love. So it's water loving. So if something loves water, it's going to be able to dissolve in it. If something is water hating, which would be hydrophobia, right? So like phobia or hydrophobic. Phobia means like a fear of something. So it's water fearing. If something is hydrophobic, it doesn't mix well with water. Think of oil in a glass of water. The oil isn't going to dissolve. It just stays in this little bubbly blob, right? And it's a little oily, bubbly blob. That's not what happens with carbohydrates. This is why if we put a teaspoon of sugar in a glass of water, that sugar is going to dissolve, right? So almost all carbohydrates are hydrophilic. The building blocks, so here we start talking about the actual building blocks of the carbohydrates. And remember, the building blocks themselves are considered simple sugars, and so they're also technically considered carbohydrates, right? So we have building block carbohydrates, which are known as monosaccharide carbohydrates, and then we have the bigger carbohydrates, which are called polysaccharide carbohydrates. So monosaccharides, these are your monomers, your building blocks, your individual subunits. These are the building blocks of the carbohydrates, and the monomers are usually sometimes even called simple sugars. An example of a monosaccharide is something like glucose, fructose as well. You may have heard of this sugar, right? It's a sugar that we find in fruit. Fructose, ribose is one, deoxyribose is one. Lots of different kinds of monosaccharides exist. So kind of imagine all these beads, they're very similar to each other, but they just have a few nuances. They have a couple of differences between each other. Like this, like I mentioned before, this bead is brown, this bead is yellow. Okay, it's the same thing. One monosaccharide is glucose, the other monosaccharide can be fructose. It can also be a chain of only glucose. That carbohydrate is going to be its specific own thing. It could be a chain of only fructose, and then that resulting big carbohydrate is going to be its own thing as well. So with monosaccharides, they are the actual monomers, so you can't break them down any farther, right? You can't go any farther. All of these monosaccharides exist in ring formats when in water, or chain formats. Chain form, ring form. Sorry. Okay. When they're in water, they actually kind of cyclize. They form a circle. Monosaccharides, especially glucose, are the main fuels for cellular work. So monosaccharides do have a role, and that role is when we eat our food, like our pasta or whatever, our body digests it and makes the pasta, that big carbohydrate, into its individual monosaccharides, and then those individual monosaccharides are used to fuel the body to carry out cellular work. So basically to give energy to the body to carry out whatever mechanisms need to happen in the cell. Most of them have 5 or 6 carbons, right? So they could be in their linear format, or when they're in water, they can form an aromatic ring. They can form an actual ring structure. One thing about monosaccharides is that a lot of them are actually isomers of each other. Okay, isomers. Do not get this word confused with a similar word that we saw, isotopes, right? We saw that, we came across it in chapter 2. Isotopes have to do with atoms and their neutrons. These are isomers. So isomers now are the actual monosaccharides, so a big molecule, okay? And it actually has to do with the fact that certain monosaccharides have the same the same molecular formula. So if you see here, glucose is C6H12O6. Fructose is also C6H12O6. And you're like, wait, what? So if I give you C6H12O6, you cannot tell me for certain if it's glucose or fructose. You have no idea. However, even though their molecular formulas are the same, their actual structure is different, right? And this goes back to one of those themes that we looked at in chapter 1, where structure dictates function. Just a small change in structure is going to completely change the molecule. So we have a glucose structure where we have this carboxyl like functional group right on the end. And then here the carboxyl group is kind of more in between, like we found embedded within this carbon framework. And that's what gives us fructose, okay? So both of these can be found in like sports drinks. Fructose is found in food. Both of these simple sugars or monosaccharides are also found in honey, and they are isomers. So isomers are, again, compounds with the same molecular formula, but different structures and properties. So because of their molecular shapes, their structural shape is a little bit different, even though it seems seemingly insignificant and looks very small as like the actual change, it's still a big deal, right? Because this dictates how they react with other kinds of molecules. So it's really important. So in the world of monosaccharides, we do have isomers. Okay, now, oops, sorry. When we have two monosaccharides that come together, remember, we can form a covalent bond between two monosaccharides or monomers, right? But in this case, we're talking about carbohydrates, so the monomer is specific and is known as a monosaccharide. When one monosaccharide joins to another, we now have two, right? And so we call this two sugar molecule a disaccharide, di-2, okay? A disaccharide is just basically two monosaccharides that are put together. An example is maltose. We have maltose is just the addition of one glucose molecule plus another glucose molecule. We have the glucose and fructose that gives us sucrose. A disaccharide you guys are probably familiar with is lactose. Have you guys ever heard of lactose? There's a couple of people out there that are lactose intolerant. This is usually a sugar that we find in dairy products. So lactose is just the monosaccharide glucose and another monosaccharide called galactose, which is like the coolest sounding monosaccharide out there, in my opinion. Okay, so, and that's just what it is. It's just a disaccharide. So these are two monosaccharides covalently bonded to each other. We already know what reaction is needed in order to bind the two monosaccharides together, right? This reaction is known as a dehydration reaction. Okay, so with a dehydration reaction, we remove a molecule of water, so we remove a hydrogen from one monosaccharide and a hydroxyl group from another monosaccharide, and this gives us a water molecule. And as we remove those three atoms to form that water molecule, the two monomers, or the two monosaccharides in this specific example, boop, come together. Okay, when they do, notice again that all atoms in a chemical reaction are always accounted for. So the atoms that we have in the reactants or the inputs are always going to be the same. The number of atoms and the type of atoms are always going to be the same in the product. This is known as a law of conservation. I meant to say, sorry, conservation, the law of conservation. This is when matter can neither be created nor destroyed, and every single atom is always accounted for after that little yield arrow, okay? So more examples of disaccharides, we have lactose in milk, maltose in things like beer, sucrose and table sugar, and all sorts of, and in plant sap as well. So things like maple syrup, right? So this right here just kind of shows you how we have two individual building blocks or two individual monomers. We're talking about, again, carbohydrates here. So these monomers are known as monosaccharides. And when the monosaccharides need to come together, they go through a dehydration reaction. This dehydration reaction removes the water molecule, okay? And so once we go through a dehydration reaction, we now join the two monosaccharides. We form a disaccharide because there's two monosaccharides. If we want to break down this monosaccharide, this disaccharide, if we want to break down this disaccharide into its individual monosaccharides, we need to go through a process of hydrolysis. So people that are actually lactose intolerant, remember how I told you how lactose is a specific disaccharide? People who are lactose intolerant, when they take in lactose, they cannot go through hydrolysis. They cannot break down the lactose into its individual monosaccharides. And therefore the lactose kind of builds up in their tummy and a bunch of different symptoms arise, right? So definitely something that could interest you. This is a video, and I'm not going to play it in this lecture right now, in this recorded lecture, but this video is as every single PowerPoint. If the PowerPoint's available to you, this video is also available to you. So I definitely would give it a watch if I were you. So now that we saw disaccharides, we're going to move on to the bigger, more complex kind of carbohydrates, and these are known as polysaccharides. So poly meaning many, right? Polysaccharide. Now, polysaccharides are complex carbohydrates. These are made of long chains of sugars, and so they're made of many, many monosaccharides. So way too many for us to even count. Okay? They could be straight or linear. They could be branched. They can be made of many kinds of monosaccharides, or they can be made of the same monosaccharide repeated over and over and over again. You're going to need to know a few examples in detail about that are specifically polysaccharides. Cellulose is one, starch, glycogen, and then chitin as well, okay? Your book doesn't actually, I don't believe your book talks about chitin, but I'll briefly explain it in just a little bit because it's kind of interesting. It's actually disgustingly interesting. Okay, so polysaccharides. So we've looked at monosaccharides. Those are the building blocks. The building blocks, when we have two of them, we get a disaccharide. And then when we have many of them, we get a polysaccharide. So let's look at the actual examples of polysaccharides. So cellulose. Cellulose is a complex carbohydrate. It's a polysaccharide found in plants. Okay, and this is necessary for their structural material. This gives them structure. Okay, this is what makes the plants stand up against gravity, and it gives that fibrous kind of consistency to the stem of the plants and to the plant in general. It's found a lot in cotton, paper, wood, etc. It gives strength and shape to the plants. Cellulose plus another component known as lignin, it actually makes up a component of the plant cells called the cell wall, where so around every single plant cell, not animal cell, but only plant cells, they have this barrier around the cell called the cell wall, and that just basically strengthens the cell, right? This is the most abundant carbohydrate in the world. If you look around you, every single plant in this world, be it grass, trees, a rose bush, whatever, has cellulose in it, and therefore it's the most abundant one. This is tough, indigestible, insoluble fiber. Okay, so this is actually really good. Even though we can't digest it, this is the stuff that cleans out our gut, right? This is things that we need to eat. We need to eat our veggies and all that stuff because The things that we then excrete, most of it is basically cellulose. And as it goes through our gut, it basically, in our tummies and all that stuff, it kind of scrapes away all the stuff that we want to get rid of. So indigestible insoluble fiber is a really good thing. Okay, so cellulose is necessary for structure, okay, gives structural support, and is found in plants. So when we look at cellulose, the actual structure of cellulose is just glucose monomers, so the monosaccharide glucose, repeated over and over and over again. And basically what they do is that they line up on top of each other. Okay, they are basically parallel on top of each other, and they form kind of like, see how they're like really strong. Like if you were to ever lay foundations on a house, or build a house brick by brick, you would basically put the bricks on top of each other. That would give you a very strong foundation. This is what cellulose is, right? Its role is in the structure, and therefore its actual configuration is 3D shape, fits its role. Remember, in biology, structure dictates function. So because it basically is lying on top of each other, we have these parallel strips of just glucose repeated over and over again. Cellulose is really tough, and it denotes strength and structure to the plant. Starch, on the other hand, starch is also found in plants. If you think of starch, you may think immediately of something like potatoes, right? Starch is also found in plants, but you can see how the structure of starch is vastly different from the structure of cellulose. It's very helical, right? You wouldn't build a house this way, because it would not basically hold. So starch does not have any role in actual strength or support of the plant. What happens is actually the starch in plants is mainly used as an energy reservoir, right? So the plant, whenever it needs a little bit of energy, if you remember, monosaccharides provide the fuel and the energy for cellular processes. It just takes one of these off of the starch. The plant takes one of these little orange, which the orange thing, by the way, is glucose. It just takes one of these little orange things off of the starch, and boom, it has energy. And this helical structure just makes it easier for the plant to basically snip at the ends of this helical structure. And so it's an easy way to gain access to energy. Okay, so starch is another complex carbohydrate, also known as a polysaccharide, found in plants again. Okay, and this time it's necessary for carbohydrate storage or energy storage. This is found in potatoes, rice, carrots, corn, etc. And this, unlike cellulose, is very easily digestible, right? You can easily digest this. There's no insoluble fiber in it. All right, so next polysaccharide we're going to talk about is glycogen. Glycogen is found in animals. It basically acts as starch. Okay, it's a carbohydrate storage, so it stores carbohydrates for like our energy reservoir, but in animals. Okay, so a lot of times, if you're like me, I usually eat more than I have to, right? More than my body needs. And when that happens, my body is going to store that food that I eat, or those carbohydrates, for example, in this particular situation, those carbohydrates that I eat for a bad day, right? For a day when I actually need this energy. Sometimes I may actually never need this energy, and that's when we start gaining a little bit of weight, but that's another story. Okay, so when we have these, we need these energy reservoirs because, our bodies are saving it. Like they know that, sometimes we need this, we go on like survival mode, and we'll need to actually tap into these reservoirs. And so our carbohydrate storage in the animals is known as glycogen. This is something that we usually find in the liver and in our muscles. So our glycogen gets deposits in the liver and in our muscles. It's basically known as animal starch because it acts the same way. The starches we eat are broken down into glucose. So any kind of carbohydrate that we eat, so if we eat potatoes or whatever, they're broken down into glucose and then added to the glycogen storage or used as energy source. So if we don't use it immediately as an energy source, it gets put into a glycogen storage. If you look at the structure of the actual glycogen, again, you see it's very like branched. This is perfect, right? This is perfect for what glycogen actually does. You can snip little orange glucose molecules to still basically a repeat of glucose. You can take little glucose molecules out of whichever end, right? It's very easily accessible. So it's a very easy way of getting energy from that reservoir of energy. So the branching also allows for better packing for storage. More glucose can fit. So when blood sugar levels drop, liver cells degrade a little bit of glycogen and they release some glucose, and so we can actually have glucose. So these are the three common types of polysaccharides. We have starch and cellulose, which are found in plants. You'll need to know what each one does. So starch is there for energy storage. Cellulose is for structure. And you can see, look at the actual like structure of cellulose. You see how tightly packed it is. It's incredible, right? This is definitely there for structure. And then glycogen is found in animals. If you can see, this arrow points to the actual human being. It's found in animals, and this is also our storage, our carbohydrate storage. The other one that I mentioned that your book doesn't is chitin. Chitin is also a polysaccharide. We do not eat this chitin, like this polysaccharide, unlike basically the other ones. We don't eat this polysaccharide. If we did, we'd basically break our teeth, and it would be kind of disgusting, to tell you the truth. This is basically, again, just repeats of glucose, but the only difference is that they have nitrogen embedded within them. So they're nitrogen containing groups. If you see here, this is our normal glucose, but you can see this extra nitrogen, right? So just that addition of that atom or of that element completely changes the actual polysaccharide. And this chitin also is there for structure and strength support, but it's for strength support for things like invertebrates, like the exoskeleton of arthropods. So the exoskeleton, like that hard shell thing, right, of lobsters or of crabs or of insects like ticks, right? And so this is the thing I was talking about. This whole structure right here is made out of chitin, and it's a very, very strong thing, right? It can also make the cell walls, which is again just that barrier around the cell of many fungi. It gives strength and shape to the structure of the organism. Okay, so that is it for carbohydrates, and I'll make another video for lipids. I shall see you guys later. Actually, no, hold on. I'm sorry, that was me giving you false hope. I'm gonna go over really quickly a quick explanation of carbohydrates right in front of me, right? Really quickly, I'm going to do what's called a concept map. This is something that I tell my students to do every single time because it's a fantastic way to study, right? So carbohydrates, you start out here with carbohydrates. The first thing you'll need to know is the actual building block of the carbohydrates, which are known as monosaccharides. Okay. Eventually my camera is actually going to focus, I'm sorry. So I have carbohydrates. They are going to, the building blocks are known as monosaccharides. If you want, you can give some examples like glucose and fructose, right? We also have, and what's actually from here, tell me what the role of the monosaccharide is. They provide fuel or energy for the cell, right? Another kind of carbohydrate is when we have a disaccharide. So here we have two monosaccharides. Examples include things like lactose or maltose. How do we get two? We get two through a process known as a dehydration reaction, right? RXN is just me abbreviating the word reaction. And then we have polysaccharides. Polysaccharides, oops, double C, sorry, saccharides, okay? These are also known as your complex carbs. Your monosaccharides back here, this reminds me of something, are called your simple carbs or your simple sugars. Okay, your polysaccharides, we have 4 of them. Okay, that's going to be your cellulose, which is found in plants and is important for structure and support and strength of the plant. Then we have starch, which is also found in plants, and that's important for storage of energy. Then we have glycogen, which hopefully you guys remember is found in animals, and that's important for storage of energy. And then we have chitin, which is also found in animals and in fungi as well, and it's important for structure and support. So this is kind of a way, this is known as a concept map. Okay, basically everything I just said, I boiled it down to like 2 minutes of just, you know, of this little one piece paper. And it's a really good way of basically taking a step back and looking at how everything connects, because this is the main thing, the main issue that students have is they have difficulties connecting concepts in biology. So now I'll finally end this part, this lecture, and I'll see you guys in the next video.